Hello everyone, today we'll be discussing the question that says f of z is equal to z squared plus z plus 1, and I'm going to determine the set of points m where f of z is pure imaginary. Firstly, we know that z is equal to x plus iy, and then we replace z by x plus iy, getting us x squared minus y squared plus x plus 1 plus I into 2xy plus y, and this is after expanding and taking the I as common. Secondly, we know that this part would be the pure part, while this part the imaginary part, because this part has I. So, what does pure imaginary mean? It means that the pure part is equal to 0, while the imaginary part is not equal to 0. If we go here, so basically 2xy plus y is equal to 0, that's the part that we do not want. So, 2xy equal to negative y, x equal to negative half, and for every y belongs to R. What does that mean? Meaning if x is negative half, this equation with 2xy plus y would be 0 no matter what y is. And here we have m does not belong to x equal to negative half. Now let's move on to the second part of this, which is x squared minus y squared plus x plus 1 is equal to 0. For us, moving on now to x squared minus x squared minus y squared plus x plus 1 is equal to 0. Here there's two ways in fact to solve it. Let's look at the first way, which is taking y to this side here and then solving it. So basically it would be y squared is equal to x squared plus x plus 1, and getting us y equal to plus 1 minus radical x squared plus x plus 1. That's the first equation that we have. Now let's move on to the second equation, or sorry, the second way to solve it. Basically, we need to complete the square of x squared plus x. Basically, what would that be? It would be plus, it would be x squared plus x plus 1 over 4 minus 1 over 4 minus y squared plus 1 to be equal to 0. So then this would give us the perfect square of x plus half all square minus y square plus 3 over 4 equals 0, getting us at the end x plus half all square minus y square equal to negative 3 over 4. Well, we can say that if you want a bitten structure, this represents x plus a all square plus y plus b all square is equal to r square. But here we have a couple of problems. First is the negative y square, and then the second problem we have here is the r squared is equal to negative 3 over 4. Well, what do we do in this case then? We are now going to continue with the equation, which is x plus half all square minus y square equal to negative 3 over 4. But we're going to look at it from a different approach, which is we're going to write plus y square I squared. It's the same thing as saying minus y squared. So now we're going to put it equal to 3 over 4 I squared. That is correct, and this, if we draw all of this, if we draw all of this, it would give us a circle. Well, let's look at this circle. But before, let's place all the points, which are, firstly, we have y equal to plus or minus radical x squared plus x plus 1. Let's place these three and see what they look like. Okay, well, firstly, we have first thing that we said is y equal to radical x x squared plus x plus 1 plus 1. So this is the first equation. Let's look at the second equation that we have, which is same thing, y equal to negative radical x squared plus x plus 1. And then we have finally the circle that we have, which we're going to exclude I out of it. Basically from this we're going to be taking the I squared out of it, giving us the circle. Where is it? X plus half all squared plus y squared is equal to 3 over 4. And as you can see, it fits perfectly between the red and blue. And that is amazing, because it fits right there in the center. But can we look at the same equation, the one that we used here? X plus half squared plus y squared I squared equal to 3 over 4 I squared. Well, if we take it back to its original form, which is instead of having an I, we replace this with a negative. Instead of having an I, we put a negative here. Can we draw that? And if we try drawing that, would we get a circle? So we started off with the equation now, x plus half all squared plus y squared is equal to 3 over 4. And then we can say, can't we say that all this is the same as saying x plus half all squared plus y squared minus 3 over 4 is equal to 0. But can't we say this is a special case of this equation? W is equal to x plus half all squared plus y squared minus 3 over 4 here, where w is equal to 0. Basically, we need to put 2 inputs then to get 1 output. 2 inputs to get an output. So meaning, here we'd have a third dimension, x, y, and then here w. Let's look at this in graphical form, in this three-dimensional plane, where this is the x, this is the y, and this is the w. Okay, well this is the w is equal to x plus half all squared plus y squared minus 3 over 4. Okay, it looks like this. Well, isn't this? Then this one should be a special case, the red one should be a special case of the blue one. In fact, it is. As you can see, the red one is just a special case of that one, where w is 0. And, well, what does this mean? Basically what happens in this one is that the w is 0. So no matter what the value of w is, it doesn't go left and it doesn't go right. The x and y stay stable, since the w does not affect it. The w does not affect the points, like here, making them go wider, or making them go back. Because if you have w is 1, then it might increase, like, make the x 2, but here, in this one, if the x is 1 and the y is 1, then no matter what the z is, or the w, because most of them take it as z, no matter what the w is, it's not going to affect those. It's going to be x1, y1, z1, z2, z3, z4, doesn't matter. So that is why here we see it more outwards, while this one's more shrinked. Okay? Well, can't we just make sure that the things that we wrote at the beginning, the equations that we wrote, y equal to radical x squared plus x plus 1 and y equal to negative radical x squared plus x plus 1 are correct? That what we drew before is correct. Here, as we can see, it's correct. It goes from here, and it goes from here. Okay. This is really interesting. Let's go back here. The initial equation was x plus half all squared minus y squared plus 3 over 4 equal to 0. Also, can't we say this is a special case where r equal to 0 and the r is equal to this whole equation? That is correct. Now let's look at it deeper. Okay, let's remove these two because we know. We'll look at them later in their relation with this. But let's look at here. R is equal to x plus half all squared minus y squared plus 3 over 4. Look how it looks. Okay, this is really interesting now. This looks different than what we expected. Because what we expected is that not really this to look like this. Well, okay, till now we can make a hypothesis that x plus half all squared minus y squared plus 3 over 4 equal to 0 is not the same drawing wise as x plus half all squared plus y squared minus 3 over 4 equal to 0, because this one has to be a subset of this drawing that we're saying, and this one was a cylinder, a subset of this one, or not really a subset, it's more of a special case. So here it's a special case, and what can we see? Look at the red lines. It is a special case. Well, okay, that's really interesting now. That what we see here in this one, in the cylinder, it fits perfectly just like we suspected. But it fits perfectly into the exact equation, which is x plus half all squared, which is the initial equation. What does this mean? Let's look at it even more. That this is the same as the cylinder. Here, the r is 0. So no matter what the r is, it doesn't affect. Here it's like saying r is 0, or if we want to put it the same way, it's like saying 0. Right, put in green. 0 r. Bring it here, doesn't matter, because no matter what the value of r is, no matter what this one is, it won't affect these ones. So if x is 1 and y is 1, r won't be really affected. So, as you can see, this is really fascinating. So, okay. This is a good thing to see. Let's look into it deeper. Let's look at our initial equation that we said we'll get back to. This one and this one. Look how they fit perfectly. As we can see, the bluish purple line fitting perfectly on the red here, and this one on the red here. Well, what does this mean? If the initial equation that we made, which is this one, is not really the true one. It's this one that we need to be looking at, and it gives us this, giving us these red, if you want, barriers or lines going above the second dimension, going up into the third. But why couldn't we see this before? It's because the second dimension is just the shadow of the third. The second dimension shows us everything from the top. I think the biggest example through what I was seeing, through what I was able to look at perspective-wise, is this one. If we look at it from here, it looks like this. Well, if we look at it from the top, if you look at it from the top, look how it looks. It looks much more different than the actual one we were looking at before. Okay. So look at it. This one is it's so different. As you can see, it doesn't, like here, the blue doesn't go on it. It doesn't touch the x or y axis on this point. But if we look at it from the top, it looks like it does. This is just a shadow or an illusion in some way. Well, okay. What does this mean? Our initial equation was to find x squared minus y squared plus x plus 1. It wasn't to find whatever I just found. Okay, that is correct. And let us use this thing that we've used a lot now, which is say that x squared plus x plus, plus 1 minus y squared equal to 0 is just a special case of z equal to 0, where z is equal to x squared plus x plus 1 minus y squared. Okay, are we getting somewhere? That's important. Well, let's look at it graphically. Looking at x squared minus y squared plus x plus 1 graphically shows us this. Wait a second. Isn't this familiar to us? Wait, let's try to line these up. Doesn't it look like x plus half all squared minus y squared plus minus y squared plus 3 over 4 not equal to 0? Yes. They are the exact same drawing. Okay. Let's continue now. Let's look at the more important thing, which is when it's equal to 0, what does it give us? The exact same lines going up here, bring this one to 0, gives us the exact same line. So what does this mean? Well, what does this being a special case? Let's also compare it to this. So we just make sure that everything is the same. Okay, let's remove this. Put this. They're the exact same. They're the exact same drawings. So what does this mean? Whatever circle we drew before, whatever sphere circle, it's just us taking a special case. Us excluding the I squared that we did, excluding it and just taking it as this form. This form that we used. Okay. Well, what is the answer then? We did all this, we looked at it geometrically, and we looked at like everything. So what does this mean? What is the answer to the question? The answer to the question is this. This is the answer. Or this is the answer. Or if you want this. No, not so. This. This. When it's equal to 0. Alright, this one, yeah. This one. When it's equal to 0, same exact line. That's really fascinating. So this is, so M belongs to these. It does not belong to whatever we found before like this. Since here we take the special case. This special case. Where the y squared is before it a plus and the 3 over 4 is before it a plus. But if you want to look at the true nature of all this, this is how it looks. In 3-dimensional space. This is how it looks. And if you want to look at the bigger picture, the much bigger picture of it not being a special case just equal to 0, this is how it looks. But for our question, to answer our question, what M belongs to this line. These. And it extends above to this z-axis. Let's look above it from the top. Wait a second. It goes. Why? Because this equation that goes up into the z-axis, when you look at it from the top, it's like you're looking at it from an x, or depending on whether you look at it, but it says this is a y plane and this is the x plane. This is how we're looking at it. This. Different angles, of course, but it's the same thing. Then as we go down little by little, these start to come up, and we look at it from this perspective now. So as you can see, this is the answer to our question. And the sphere that we drew before was just a special case that we made, and it does not actually exist in the answer of the problem. And as we can see that there is a third dimension that we don't take into consideration, and it's just a shadow, and the second dimension is just a shadow of that dimension. Thank you very much.